So the next thing that we have here is there is a part here that talks about shortcut method to find variance and standard deviation. Let's see what that is. So sometimes the values of x of I in a discrete distribution, or the midpoints x of I of different classes in a continuous distribution, are large, and so the calculation of mean and variance becomes tedious and time consuming. By using step deviation method, it's possible to simplify the procedure, which is of course very helpful sometimes. Let the assumed mean be A and the scale be reduced to basically 1 to h basically times, meaning h being the width of the class interval. Let the step deviations or new values be y of I. That is, y of I is equal to, so basically, I have to start from the very beginning. So let's say that you have all of these x of i's. So either you have a discrete distribution or a continuous distribution. So basically we said that we had the discrete basically frequency distribution, and then we had also the continuous frequency distribution. Now, in case you have a discrete frequency distribution, you have your data in this way, meaning that you have, for example, you have your x of i's over here. And your x of i's would be, for example, x1, x2, x3, all the way up to x of n. And then you have the frequency related to these, which are, for example, f1, f2, f3, all the way up to f of n. And then, for example, if you want to calculate sigma, for example, then sigma, as you know, is equal to, for example, 1 over n times the square root of n times, for example, sigma f of I times x of I, whole squared, not whole squared but squared, as I goes from 1 to n, minus sigma of f of I, x of I, as I goes from 1 to n, and you raise this to the second power, take the square root of this whole thing, and that becomes your sigma. So then in that case, if you want to calculate, for example, standard deviation, that would be your formula. Now here you can see that you have to use, for example, your x of I and multiply it by f of I, and in different parts of this formula. So what you need to do is that so the formula of course remains the same, and this is called a discrete frequency distribution because you have all of your observations right over here. Now sometimes what happens is that your observations are not given to you that way. Sometimes you have these classes. And these classes go from, for example, x1 to x2, then x2, for example, to x3, then you go from x3 to x4, and all the way up to, for example, x of n minus 1 all the way up to x sub n. So in this case, again, you need to, what you need to do in order to find your x sub I is, again, you take, for example, the average of these two, x1 plus x2, for example, divided by 2, or x2 plus x3 divided by 2, and so on and so forth. Now, in the assumed mean method, we came basically in the x sub i's, whether you have your x sub i's in this way, basically as the average of these classes, the upper limit and the lower limit of these classes, or whether you have your x sub i's directly, you will have access to some x sub i's here. Now in the assume mean method, we took some value over here in the middle as the assumed mean, and we called it a, for example. And of course then all of these x sub i's that you have here, you subtract a from it so that these x sub i's become smaller. And then sometimes you even divide this by your class size, so that everything, I mean, if it's possible, if your class size is h, you can divide this whole thing by class size, so that things get still basically smaller. So now in this situation, let the assumed mean be a. Let the assumed mean be a, be capital A, and the scale we reduce to 1 by h times, and the scale be reduced to 1 by h times h being the width of the class intervals, h being the width of the class intervals. Let the step deviations or the new values be, so they have called the new values, they have called it step deviation. I don't know how, but let these step deviations of course it's some deviation, meaning that, for example, you write x sub I minus a, it's some, basically it's a deviation of all of your x sub i's from the assumed mean, so you can call it a deviation or step deviation. So let the step deviations or the new values be y of i. That is y of I. You can write it as basically x sub I minus a, basically the difference between your each x sub I and the assumed mean, and then to make things still smaller, you divide it by h, or you can write basically, you can cross multiply, you will get x sub I minus a is equal to h times y of I, or you can write x sub I is equal to h times y of I plus a. So that is basically that. So, and we know that if you call this, for example, equation number 1, and also we know that x bar is equal to sigma f of I x of I as I goes from 1 to n over n. that is basically the average of some basically n observations, right? So that is basically number 2. Now if you replace x sub I from 1 in 2, if you replacing x sub I from 1 in 2, what you will get is basically x bar is equal to basically sigma f of I times x of I, which is h times y of I plus a divided by n as I goes from 1 to n. And then you need to make some arrangements here, meaning that I can write this as, for example, I can write this as 1 over n, for example, 1 over n times, for example, sigma f of I times f of I times a as I goes from 1 to n, plus sigma f of I times h times y of I, sigma h times f of I y of I as I goes from 1 to n. And I can write this as basically 1 over n times basically a times sigma f of I. So this is 8 times basically sigma f of I as I goes from 1 to n, plus h times sigma f of I y of I as I goes from 1 to n. And you know that sigma f of I as I goes from 1 to n is equal to this whole thing, sigma f of I as I goes from 1 to n is equal to capital N, right? So that is capital N. So that's the same thing as 1 over n times a times capital N plus h times, now sigma f of I y of I as I goes from 1 to n is equal to times 1 by n. That's the same thing as y bar, right? So if I write, for example, if I write sigma f of I y of I as n as I goes from 1 to n, and if I divide that by n, 1 by n times that, that's the same thing as, that would be the same thing as if I write 1 over n times sigma f of I x of I as I goes from 1 to n. And you know that this is equal to x bar. This part over here is equal to x bar. So this part over here, you can write it as y bar. So that means that this is h times, h times basically this whole expression here, but in the next step you can write it as, if I basically multiply 1 by n times this, n and n will cancel out, n and n will cancel out, and you will get just simply a, and then over here you will get h times y bar, So that means that x bar is the same thing as 8 plus h times y bar. x bar is the same thing as a plus h times y bar. Now a was the assumed mean, and y was y of I was basically the new values of x of I, right? So now what I can do is that now we said that variance is equal to variance of the variable x, variance of the variable x is sigma of x whole squared is equal to 1 over n sigma of f of I times x of I minus x bar whole squared as I goes from 1 to n. So since I have my x bar in terms of a and y bar in terms of x and y bar, I can write this as 1 over n sigma of I goes from 1 to n of f of I times x minus y x bar, which is equal to minus a minus h times y bar. And of course this is whole squared, right? And now we had some relationship over here. X of I, we wrote it as h times y of I plus a. X of I, we wrote it as h times hy of I plus a, hy of I plus a. So now everything is coming together, meaning that you can write x of I, this is x of I. I can write this as this thing over here, I can write it as 1 over n times sigma f of I times x of I, which is h y of I plus a minus h times y bar whole squared as I goes from 1 to n. Now these two will cancel out, and so you can write that as 1 over n sigma f of I is equal to 1 to n, and then you can take the h out, h times basically y of I minus y bar. Okay, and of course this is again whole squared. This is again whole squared, and then you can take this h out. You can take this h out, meaning that you can write this as h divided by n sigma f of I times y of I minus y bar whole squared as I goes from 1 to n. And I think that's it. Of course this is supposed to be h squared because h was over here raised to the second power. So this is h squared over n. So y of I minus y bar whole squared. So and of course we said that the the variance of variable x. So we said that sigma of x was equal to sigma of x whole squared, which was the variance of variable x, was equal to basically 1 divided by n sigma f of I x of I minus x bar whole squared. So you can see that this part of the formula over here is actually variance of the variable y. So you can write this as basically you can write this as h squared. You can write this as h squared times the variance of the variable y of I. So this is h squared times the variance of y of I, right? And that means that sigma of that. Let me write somewhere else. Where can I write? I need something over here, some paint, for example. So that means that I can write, and this is basically, and this whole thing was basically sigma of x whole squared, right? This was sigma of x whole squared. This is the variance of the variable x. So I can write the variance of the variable x is equal to h squared times the variance of y of I. Or I can write this as basically variance of the variable x is equal to h squared times the variance of the variable y is basically sigma of y whole squared. Or I can write basically I can write sigma of x is equal to h times sigma of y, taking the square root of both sides of the equation. Right, so that is basically one thing that we have here. And then we said that basically equation number, we had some other equation number 3, which was basically x bar was equal to a plus h times y bar. So that means that sigma of x is, you can write it as sigma of x, you can write it as sigma of y f of I y squared, and okay, 1 over n h divided by that, h times that. Okay, so that means that basically previously we said that sigma, we wrote sigma of x, for example, we wrote that we have the formula sigma of x was equal to basically 1 over n times the square root of, you do remember that formula, it's n times, for example, sigma of f of I, for example, x of I squared as I goes from 1 to n, minus sigma of f of I, for example, x of I as I goes from 1 to n. This, you raise that to the second power, you take the square root of both of the whole thing, and that was basically standard deviation that we used. So now based on this, I can write the same equation. I can rewrite this equation as basically the variance of the standard deviation of the variable x is equal to basically h times, meaning that basically if you want to write the same formula for sigma of y, you have to basically substitute every x that you see here with y. That's basically the only thing that you would have to do. And then you would have to multiply h by this whole thing. So I write this as basically h over n times the square root of, for example, n times sigma f of I. Instead of x of I write y of I whole squared as I goes from 1 to n, minus, for example, something like sigma of f of I, y of I, as I goes from 1 to n, and raise this to the second power, and that's basically the variance of the variable x. So the variance of the variable x is h divided by n times this whole thing. And over here, basically the only thing that you need to know is of course a is we don't have a anymore, but y of I is basically the new variable based on x of I, meaning that we had x of I in our data, and then we subtracted a from x of I, we got basically x of I minus a, and then divided that by the class size, which was h, for example, and that gave us y of I. So that is basically where y of I comes from in this formula, and that's the whole story. So I'm going to make a screenshot of this. I don't know where my mouse is. I'm going to make a screenshot of this, and I don't know how do you is it possible to, I don't know. Anyway, let me just make a screenshot of this part of this, and then forget about the rest of it. I'm going to okay, so I think now I can okay, I'm going to just simply okay, that's okay. I'm going to save this on desktop. I'm going to write it as statistics formula 4, for example, on desktop, and that's basically that. So that's basically the whole story here. Now let's do a couple of examples using this formula and this way of calculating the variance and the standard deviation. Let's see how we can use it. Now we have a set of data over here, which is we have some classes, and we have the frequency related to those classes. So let's say that you have basically, say that you have these classes. You have these classes, and the frequency related to those classes, let's call it f of I, for example. Let's say that your classes are, for example, 30 to 40, and then you have 40 to 50, 40 to 50, 50 to 60, 60 to 70, have 70 to 80, 80 to 90, and 90 to 100. And the frequencies related to these classes are 3, 7, 12, 15, 3, 7, 12, 15, 832, 832. And what you want to calculate here is the mean, the variance, and the standard deviation, and the standard deviation related to your data. Now what we just calculated here was basically that basically helps you calculate so basically what we said over here was that now if I calculate my x of i's here, it would be, for example, 35, that would be, for example, 45, 55, 65, 75, 85, and 95. And 95. 190, okay. Now if you want to calculate, for example, the mean over here, your x bar is going to be equal to sigma, for example, f of I x of I divided by sigma f of I. And you see that you have to multiply all of these numbers together, which is not very straightforward. Now what we need to do is, let me see how they have solved this problem. Now over here we said that x bar is equal to a plus h times y bar. Okay, so over here what we said was that basically if you have these x of i's over here, right? If you have these x of i's over here and the values of your data are not very straightforward, what you can do is that you can take the assumed mean as, for example, you can take the assumed mean as capital A, and you want to let the scale be reduced to basically 1 by h, h being the class width, and so then So then based on this, so the new values of x of I, you can call them y of I, and of course, since this is the assumed mean, you have to subtract it from your x of i's and then divide by basically the class size so that the number gets smaller. And so based on this, you can, if you cross multiply, you will get h is equal to based on this, then y of h times y of I is equal to x of I minus a. Or you can say that x of I is equal to h times y of I plus a. And then, well, if you just keep going with this formula, we said that now since x of I is equal to basically h times y of I plus a, then based on this, your x bar is going to be equal to basically this value of x of I, or sigma, basically sigma f of I. Then x of I is going to be this value h times y of I plus a divided by sigma f of I. And if you keep going with this calculation, you will get basically x bar. You will get x bar, if you just keep going with this calculation, you will get x bar is equal to a plus h times y bar. X plus h times y bar. And so in this formula, basically y of I is equal to x of I minus a divided by h. So that you can use to calculate the median of the mean of your data. And also we calculated sigma of x. We calculated the sigma of x as basically h divided by n times the square root of basically n times sigma of f of I y of I, all basically squared as I goes from 1 to n, minus sigma of basically f of I y of I, all squared, of course, as I goes from 1 to n here, and that's then basically how you calculate your sigma of x, which is basically the standard deviation of the variable x. So now I keep these two formulas and erase the rest of the things. Because we are going to need this space over here. And so now, in order, for example, to use this formula here, what I need is, again, if I were to use, for example, the table itself, it would be pretty hard to calculate my x bar here, because x bar is, as you know, is equal to sigma f of I times x of I as I goes from 1 to n over sigma f of I as I goes from 1 to n. And then over here I would need to calculate f of I times x of I. F of I times x of I is basically these values basically multiplied together as a new column here. That would be pretty simple, at least. So what I'm going to do is that I'm going to calculate, basically I need to take the assumed mean and then also the class size. So the assumed mean I'm going to take as, for example, 65. So then my y of I could calculate it as x sub I minus a. I could write this as x sub I minus a over h. So now my class size is 10, right? So my h is equal to 10 and my a is equal to 65. So now x of I, for example, 35 minus, for example, a, which is 65, divided by 10, gives me what? Gives me, for example, negative 30 divided by 10, which is equal to negative 3. That is a negative 3. 45, for example, minus 65 divided by 10 gives me negative 20 divided by 10, which is equal to negative 2. 55 minus 65, that's going to give me a negative 1. 65 minus 65, that's going to give me a 0. 75 minus 65 is equal to 10. 10 divided by 10 is equal to 1. 85, 22, and 3. So now the numbers are very small and very simple. So that is my y of I. Now we said that basically then x bar is equal to a plus h times y bar. So x bar is equal to a plus h times y bar. So I need to calculate y bar over here, right? I need to calculate y bar over here. So y bar is the same thing as as you know, since you know that x bar is equal to, for example, sigma f of I times x of I divided by sigma f of I as I goes from 1 to n, and again as I goes from 1 to n, then based on this, y bar is going to be sigma f of I times y of I over sigma f of I. So then based on this, then x bar is going to be equal to a, which is equal to 65, and h is, well, 10 times y bar, which is basically sigma f of I y of I sigma f of I y of I sigma f of I y of I divided by sigma f of I. Now over here sigma f of I is equal to what? Over here sigma f of I is equal to 10 plus, this is 22, 32, 37, 40, 50 divided by 50. And now sigma f of I y of I is equal to basically all of these numbers. So it's basically these, you can calculate that over here as well. Sigma basically, let me see, what is sigma f of I y of I? So f of I y of I is equal to basically negative 9, negative 14, negative 12, 0, 8, 6, and 6. Adding all of these numbers together, sigma f of I y of I is going to be equal to, basically that's a 12 plus 8 is equal to 20. 20, and then there here you have 26, 26, 36, 35, minus 35, that's a negative 15. That's a negative 15. So that means that then you can write this as, you can write your x bar as 65 plus 10 times negative 15 over 50, divide by 5, you'll get 3, divide by 5, you'll get 10. 10 and 10 cancel out. 65 minus 3 is equal to 62. So your x bar is equal to 62. X bar is equal to 62. You see how it's easy to calculate using these formulas. And then the rest of the calculation, so I don't really need this anymore, but this part over here I need to calculate. We calculated the mean. Now we need to calculate the variance and standard deviation. So the variance is basically sigma squared. Sigma squared, which is basically the square of this whole thing. So then sigma squared is equal to basically h squared by n squared divided, based on this formula, h squared by n squared times this whole expression here, which is n times sigma f of I y of I squared, as I goes from 1 to n, minus sigma f of I y of I as I goes from 1 to n whole squared, right? So that is your variance. That is your variance. Now, to calculate your variance, you already have your h squared, you have your n squared, you have, again, you need to calculate, for example, f of I times y of I whole squared and take the sigma of that, and you need to calculate f of I times y of I, which we have already calculated, and take the sigma of that, raise it to the second power. So this part is already done. So the only thing that we need here is f of I times y of I squared. So f of I times y of I squared. And then we need to then take the sigma of that. So then f of I times y of I squared, y of I squared over here is, for example, 9 times f of I is equal to 27. Y of I over here is 4 times 7 is equal to 28. Y of I over here is 1 times f of I is equal to 12. Y of I over here is 0 times anything is 0. Y of I over here is 1 times 8 is equal to 8. Y of I over here is 2. So 4 times 3 is equal to 12. And y of I over here is 9, and I'm sorry, y of I squared is 9. 9 times 2 is equal to 18. Now if I calculate sigma f of I y of I squared as I goes from 1 to, for example, I don't know, 6, 7, just write it as n, that's equal to basically all of these numbers added together, which is 28 here. sorry, not 28, which is 20, 30, 38 here. And then you have 12 plus 28, which is equal to 30, 40, which is 40. And then you have 27 there. So you have 15, 1. 15, 1. So you have 4 plus 4 is equal to 8 to 10. That's 105. So that is your sigma alpha by y of I whole squared. So I can write this as, I can write sigma squared. I can write sigma squared is equal to h squared, which is equal to 10 squared, which is equal to 100. N squared is equal to sigma alpha y squared, which is 2500, which is 2500 times n times, so n was basically 50 times sigma alpha by y of I squared, which is this value over here, 105 times 105, minus this value, sigma alpha by y of I squared is 15 squared is equal to 225. 15 times 15, 25, 575, 0, 15, and that is 5, 225. So that is 225. And so then this value is going to be 1 over 25. 1 over 25 times 50 times 105 is equal to 5 times 105. 105 times 5 is equal to 25. 525 with a 0, and subtract the 225 from that. You will get a 4, a 10, 5, and a 2, a 0, a 5. 5025 divided by 25. 5025 divided by 25 is equal to 5025 divided by 25 is equal to 2 times 25 is equal to 50, and 1 times 25 is equal to so 50 is 0, then you have a 2, 0, and 1 times 25 is equal to 25. So that's 201. That is equal to 201. So your variance, this is the value of your variance. Now, since your variance is equal to 201, the standard deviation, which is the same thing as sigma. The same thing as sigma is equal to, write this properly, the same thing as sigma is equal to the square root of 201, which you can calculate pretty easily. 201, group them, and then 1 times 1 is equal to 1, 1 remainder, 0, 1, and then 1 plus 1 is equal to 2. Over here you have 25 times 5 is equal to 125. 24 times 4 is equal to 16, 1, 96. So you have 4 and 4. 96. That's a 5.050. So then you have 24 plus 4 is equal to 28. And oh, sorry, you have to have 2 zeros here. These 2 zeros come down here. That becomes a 500. And then for example, you can go for 222 times 2 is 220, 280, for example, 2 times 2 would be around 560 something. So 281 times 1 is equal to 281, and remainder 280, let's say 300, 220, 219, 219. Is it correct? So that's a 4, that's a 9, that's a 10, 9, 1, and 2. And then if you go for, if you add a 1 to 281, you'll get 282. And 2 zeros here, 2 zeros here, and one basically you want to go for 22,000. So something about 7 times. So 7 times 7 is equal to 49, 4, 14, 18, 1, 56, 57, 5, 14, 19, 19,000. Okay, I think you cannot go any higher than that. So you need to go for 7 and 7 here, and you get 19,789 with some remainders here. So I take it as 14.2. 14.2, which they have taken as 14.18. If I took it as 14.2, and that's basically the whole story there. So of course in the beginning it might be a little bit confusing to use these formulas, but then if you understand how we got the formula, then you can of course use it. There is no problem with that. That is basically that. Now we have a couple of exercises here, around 10 of them, and then we have another part, analysis of frequency distribution and comparison of two frequencies with the same mean. Some exercises, miscellaneous examples, and that's it, I suppose. Okay. This is all mathematics. Okay, so in the next video we will take care of these exercises, and then we'll do the rest of them as well. I'll see you in the next video.